Good morning, students. Welcome back in your physics class. We were discussing with our topic of Bohr's atomic model, and now today we are going to discuss further in the Bohr's atomic model about some important points. We know that the orbit in which the electron will revolve will be the integral multiple of the whose angular momentum will be equal to integral multiple of nh upon 2 pi. This L can be written as mvr equal to nh upon 2 pi. This we have already discussed. After that we have discussed the radius relationship. The radius relationship of the electron was given by r is directly proportional to n square upon z. Also, we know that this r can be equal to 0.53 dot n square by z. When we talk about the velocity relationship is v is directly proportional to z by n, where the velocity formula will be v equal to 2 pi k ze square upon nh. This is the velocity formula. Now, when we talk further, we come to know that the frequency, which is the third point, the frequency is directly the formula for frequency is 4 pi z square e4 m k square upon n cube h cube. Putting the value of constants, we are getting the velocity of electron proportion to z square upon n cube. When we talk about the fourth one, we have the kinetic energy of the electron. So kinetic energy, the formula for kinetic energy is 2 pi square me4 z square k square upon n square h square. So after putting the value of constant, we get 13.6 as a number, z square upon n square. We already know, students, over here that what does this z mean, what does this n mean. Similarly over here, what does this z mean, what does this n mean. And this proportionality sign is because we have removed the whole of the constants. So that is why how we have obtained the relationship for the frequency and the kinetic energy of the emitted electron. Now let's move to the next concept, that is the potential energy of the electron. So what do you mean by potential energy of the electron? The potential energy which we are talking about, the formula for this potential energy is given by minus of 4 pi square me to the power 4 k square z square upon n square h square. Putting the values of constant, we get minus 2.72 multiplied by z square upon n square. What is the unit? The unit is electrovolt. So you have to learn this value as it is important in the numericals also. After that, when we come to the next topic, we get the total energy of the electron. So when we talk about, this is so genuine that if potential energy and kinetic energy both were proportional to z square upon n square, because the unit is always energy, so cannot we say that the actual energy, the total energy, will also be proportional to z square upon n square. And when we talk about, it is equals to minus 13.6 z square upon n square. So this is the value of total energy that you have to learn. Now let's talk about the wavelength of radiation. Emitted when the electron jumps from n2 to n1. The condition provided is that the electron is jumping from n2 to n1. So let us see. what will be the solution? We know that 1 upon lambda can be written as 2 pi square m k square e4z square upon ch cube, and here there was 1 upon n square also, but as the orbits are changing, we will write the final orbit first and then initial orbit and their square, okay, and they are in the denominators. Now when we put the whole value of this, so this comes out to be r. So r, what is r? R is the Rydberg's constant. So this is to be highlighted that this part r is Rydberg's constant for the whole value that we have got over here from our understanding. So we can write that what is the value of r? Value of r is 2 pi square m k square e4 z square upon ch cube. And when we put the values of all of these constants, this Rydberg r becomes again a constant. The value is 1.097 multiplied by 10 to the power 7 meter inverse. Now this is the value of this Rydberg's constant, and when we are putting it in our wavelength formula, we get 1 upon lambda equal to 1.097 into 10 to the power 7 1 upon n1 square minus 1 upon n2 square. So this is our formula which is to be learned. After that, if we are just substituting the formula and we are calculating the actual wavelength, what we need to do is we need to reverse all of this. Now when we talk about the frequency is always wave number is always equals to 1 upon lambda, so it will be equal to the inverse of the same that we have got. So whatever we have got in the above equation, this is also equal to this frequency on the wave number only. So I can say that whatever part we have got over here is also equal to wave number. Now let us discuss about the excitation energy. Means what do we mean by excitation energy, and also what is the meaning of the potential over here. So let's read about it. So the energy required to take an atom from its lower state to higher state is called excitation energy. Means if n equal to 1, which is a low orbit, and we have n2, which is the higher orbit, so from here to here when we have to take the electron, we have to give EE, means excitation energy. The potential through which the electron should be accelerated to gain the higher state is called excitation potential. Means when we are giving this excitation energy, what is the potential of the electron? So that is only this excitation potential. Now let us talk about the ionization energy and potential. So what are ionization energy and potential? So let's discuss about it, that what do we mean by ionization energy and the potential. So we know that ionization energy will be equal to the energy at the infinite minus energy at the nth subshell, because this will only give the ionization energy, means the energy which is required to remove the electron from its orbit, and the value comes out to be 13.6 z square upon n square electron volt. So this is the we also see that this ionization energy is kinetic energy itself, because the value of kinetic energy is same as ionization energy. When we talk about ionization potential, what do we understand by the term ionization potential? We find out from ionization potential it is equals to minus of 13.6 upon multiplied by z square upon n square volt. Now we know this, that this term which we have seen over here, this was also equal to the energy, the total energy. So cannot we say that the potential and energy are linked, like the ionization potential is equals to energy multiplied by, since it is volt and there it was electrovolt, so we can say 1.6 multiplied by 10 to the power minus 19. So this also we can say, because this is also that what we have seen from the observation. So now when we conclude, what do we get? We get that the ionization potential, which we can represent by IP, is always equal to the energy of ionization upon E. So it is 13.6 Z square upon N square volt. So this is the value of ionization potential, and you have to remember this part. Now let us talk about the de Broglie's explanation of Bohr's second postulate in our next class. That's all for the day. Thank you. Stay home, stay safe.